Okay, so we'll resume our discussion going into Chapter 4, the use of matrices to make representations in different point groups. So last time we used different kinds of bases for making representations. Maybe the most significant was the use of x, y, and z as a basis for a three-dimensional representation in the point group C2V. And we could certainly come up with any number of bases for representations, and we found that there might be simpler representations that we could come up with, as well as very large multidimensional representations. So before we answer the question of what is the simplest or most fundamental type of representation, I wanted to just show you more examples using matrices to write representations in point groups that differ from, say, C2V, where all of the symmetry elements lie on Cartesian axes or planes, right? What about angles that are not 90 degrees or 180 degrees? Things like that. So let's take a look at that. So let's imagine a point group with a C3 axis, because the C3 will go 120 degrees about the rotation, which carries something on, say, an X or Y axis off of the axis. It's not a neat 90 degree or 180 degree rotation. So in the C3V point group, you have E, you have C13, C23, sigma V1, sigma V2, sigma V3. These are grouped together in a class of order 2, and then these are grouped together in a class of order 3. Right? So you should see when you write the characters, they will all have the same character. So if you work out the transformations for one of these and figure out the character, that should be the same character for every other symmetry operation. So you only need to work out 3 transformation matrices in this case, right? So let's just go ahead and simplify this. So that we can write our representation in the point group. Right? So let's make a representation for x, y, z, which means we're going to make matrices that will transform a column matrix with 3 components, x, y, and z, to some new point. So here's our transformation matrix that we construct. This is a 3-dimensional matrix. So with the identity operation, I would write a matrix that looks like this, so that when I perform the multiplications into the column matrix, I end up with x, y, and z. So the character of the matrix is the sum of the diagonal terms in the square matrix, which is 3. Okay, so then we're immediately confronted with the C3 axis, which is a 120 degree rotation. So what happens? Make this a little bit bigger. And we'll just say we're going to use a clockwise rotation. We want to set the C3 axis on the z axis in a Cartesian coordinate system, just out of convenience. So if I draw a coordinate system so that I'm looking through the CV, or the C3 axis, I have an x-axis, say, this way, and a y-axis this way. I'm looking through z, the CV. Okay? So if I have some point on x, it will move 120 degrees, and it will have projections on the x-axis and the y-axis. And I need to account for both of those when I write the transformation matrix. Okay? So very generally, let me show you a way to handle any angle theta for rotation about a CN axis. Okay, so a very general transformation matrix. So let's say I have some point, and I'll call it R1, and I'm going to rotate about the axis that's coincident with Z by some angle theta, so that it moves the point to a new location. We can call it R2. So this is the angle theta between that I rotate. Okay? So R1 has projections along the x and y axes. And I'm going to take advantage of this, breaking it up and just look at the x and y components. So if I do that, move my theta over here just so it's out of the way. All right. So then I can call this point here x1, for example, and then this point here, the projection on the y-axis, y1. Okay? And then when I move to R2, I have new projections that would be x2 and y2. Well, let's just take the x1 component of R1, and let's rotate that by theta. So maybe a different color here can help us to see what's going on. So if I rotate just x1 by theta, I have these intermediate projections that I need to account for. Okay, so I can call that, say, x prime, and this projection on y, y prime. Now this y1 projection from the starting point of R1 will also rotate by the same angle theta, and it's going to move somewhere over here, let's say. And then it's going to have its new projections on the x and y axes. So we can call this x double prime, and we can call this y double prime. So I'm going to deconstruct and then recombine. So when R1 goes to R2, R1, of course, is made up of x1, y1. And then x1 is going to be transformed to a new location that has the components x prime, y prime. Right? And then y1, so I'm decomposing R1 to x1 and y1. When y1 is rotated, it goes to the new projections x double prime and y double prime. Okay? Such that the new point, R2, which has its projections down here, let's go back to the blue color. R2 will have its projections on the x and y axes. We'll call that x2 and y2. So the x2 is going to be the sum of these deconstructed components. And y2 is equal to the sum of these deconstructed components, y prime and y double prime. Okay? So it's kind of weird. I'm going to take this, R1, break it up into its x and y components. I'll rotate those x and y components, which generate new projections, x prime, x double prime, y double prime. And then when I recombine them, so I'll recombine the x components to get the second point projection of R2 along x, and I combine the y prime, y double prime components now to get the y2 projection of R2 on the y-axis. So if you can do that, then you can figure out, since R2 is equal to x2, y2, x prime, so that's the projection of x1 after the rotation by theta back onto the x-axis. It is the, so if x1 is the hypotenuse now, then x1 is the cosine of x1. Okay? So the triangle that I'm representing is the triangle that goes from the origin to the rotated x1 back to the projection of x1 on the x-axis to give x prime. Okay? So this triangle here, the cosine of this angle theta so that's the hypotenuse. Cosine of x1 gives you x prime. Okay? Similarly, for the y prime, since I'm rotating by theta, I generate another triangle. Y prime is equal to y1 cosine theta. Oops, sorry about that. Sine theta. Why is that? So y1 is rotating by theta. And I'm confusing myself. Y prime is derived from x1 being rotated by theta, and then we're looking at the projection y prime on this y-axis, which is going to be the sine, or this length of the triangle. So sine theta gives you the projection y prime, which is what we're solving for, on the y-axis. Okay? So now we know x prime and y prime. X double prime is going to be, so I'm taking now the projection of R1 along y, which is y1, right? I took y1 and rotated it by theta, and now I need to work out the projection on the x-axis. So the triangle that I'm working with is this one. I need to know this distance here, which is the same as this distance. And then I need to know this distance here, which is the same as this. So the x component is, if this is theta, then I need the sine of theta times y1. And notice that when I do this, I have a negative. I'm projecting on the negative side of the x-axis. Okay? So that y component, if I take the magnitude of sine theta, it gives me this distance, but I need to put a minus sign because I'm this side of the x-axis. Y double prime is this distance here, which is y1 times cosine theta. Okay? So I think I've got everything. This is a mistake. So that should be x1. Okay, so I deconstruct R1 to x and y projections. I'll separately rotate the x projection and work out these new projections, x prime, y prime. Okay, I keep those in my pocket. And then I'll take the y projection of R1, rotate it by theta. I get the new projections, x prime, double prime, y double prime. I've got those in my pocket. I'm going to recombine the now I'm going to recombine these so that I get x2, y2. x2 is x prime, x double prime. So when I add those together, that's going to be x1 cosine theta plus, since this is a negative, so minus y1 sine theta. And then y2 is equal to the y prime, y double prime, so x1 sine theta plus y1 cosine theta. Okay? And now we can write the transformation matrix. We start with x1, y1, z1. We're going to go to x2, y2, z2, which is equal to x1 cosine theta minus y1 sine theta. And then y2 is x1 sine theta plus y1 cosine theta. And then z2, since the rotation is in the z-axis, the z component is unchanged. So it's just going to be z. Okay? So then that allows us to write a transformation matrix to get these elements of the column matrix that represent the new point R2. Okay? And so we have cosine theta minus y sine theta, and then sine theta, cosine theta, and then 0, 0, 0, 0, 1. So that should be your transformation matrix for a clockwise rotation about C3, where theta equals 2 pi over 3 radians, or 120 degrees. Okay? So it's kind of a tricky explanation. Yep.
Isn't that counterclockwise though?
Oh, sorry. I did a counterclockwise rotation. Yep, that's right. So I did counterclockwise. Why did I do that? I don't know. Yep. So I worked out a counterclockwise rotation, and so if I do a clockwise rotation, everything's exactly the same. What happens is the minus sign component is here, and this is positive. Okay. So that's all you have to do. If you go clockwise, this is positive, this is negative. If you go counterclockwise, that's negative, this is positive. Okay? So you'll have to work this out if you want to convince yourself that this is true. So there's two ways to go about this. You can either just say, okay, here's the transformation matrix for a Cn aligned with the z-axis, and you can just say, I accept it, I don't care about the machinery, great, perfect, I have it. If you want to, and I think it's more satisfying, is wrestle with this. Try to take a vector R1, break it down to x1 and y1, rotate the x1 and see its new projections, which I just called x prime, y prime, and then take the y1 projection, rotate it by theta, find its new projections, x double prime and y double prime, add those together to get the new points x2 and y2, which define the point R2. So if you try that on your own, you'll understand why you see the terms in this transformation matrix. Okay? Why do we have to go through that exercise? Because we need the character for the representation in this point group. So the character is the sum of the terms on the diagonal. So cosine of 120, if you just take a circle, right? 100. If I take a 120 degrees rotation counterclockwise, then the projection back on the x-axis is the cosine theta, which is -1/2. Okay, so we have -1/2 plus -1/2 plus 1 equals 0. So we need to do this trigonometric work so that we can write a transformation matrix. From the transformation matrix, we can now plug in any value theta, work out the cosines, and add up the terms in the diagonal. That gives you the character of the matrix. The character goes under the class of C3 symmetry operations. I only need to work out one. The character should be the same for any one of the C3s. And very clearly, if I had done a 240-degree rotation, which brings me here, I get a triangle that projects back on the x by -1/2. So I do get the same values here, -1/2, -1/2, 1, which gives a sum of 0. So the characters match for all symmetry operations in this class. Okay? Any questions on that? So I think this part is confusing at first, and the best way to really understand it is to work it out for yourself on paper, and you can convince yourself that this is true, and that it allows you to formulate this transformation matrix. Otherwise, if this is throwing you off, move on. Don't spend your time with this. It's nice if you can understand this, because it gives you the machinery behind this transformation matrix and why it works. If you don't like that, you can just say, okay, here's my transformation matrix. This type of transformation matrix always represents Cn along the z-axis.
So if we have to work around the x-axis or y-axis, where have to we change in that?
So all you do is interchange the components, right? So if it's aligned along x, then this component would be 1, and the y and z components move about the axis, right? It gets a lot more complicated if you have CNs that are in between axes, not necessarily bisecting them, but at odd angles. You get into some complicated geometry. That's not the objective here. And in fact, in most cases, they're not even relevant in chemistry. The main off-axis type of rotations that you're worried about are the C3s that are found in the cubic point groups. And I've shown you how x, y, and z transform with those C3s. If I have time, I'll show you again so that you see what that looks like. But basically, the function of those C3s is just to take x, y, and z and move them into one of the others, x, y, or z, either positive or negative. Okay? So they aren't as bad as they might seem at first, and probably the worst, I guess not worst, but the most maybe intimidating transformation matrix that you will encounter would be something like this, a Cn aligned along one of the axes where the rotation angle is not 90 or 180 degrees, because then you have to think about, oh, it's some other angle, theta. I have to think about the trigonometric functions. Okay. All right, so we have transformation matrices for rotations, Cn, which allowed us to get the character in this representation. That's cool. All right. Now we need the characters for the sigma v's. This problem might seem challenging at first because we have some sigma v's that may not be aligned along particular Cartesian axes or planes. However, because we know that the character is the same for every symmetry operation, we can conveniently pick one of the sigma v's aligned with the xz plane, right? And we know that transformation matrix. That's very simple. So the transformation matrix for the reflection about the sigma xz plane looks like this. Because I take the point x, y, z, x and z stay the same, I reflect the y component. And of course, the character of this then, 1 plus 1 minus 1 equals 1. So I only need to solve one mirror plane. The character will be the same for the other two mirror planes. Now you'll have the transformation matrix for those other planes looks something like this. It's a little bit different. In fact, I had meant to make copies as handouts for you, and I can do that immediately after class. If you'll have the patience to wait for copies, I can give it to you right after class, or I'll just give it to you on Friday. But I basically have a sheet which has this written out for you. Okay? All right, so that's how we can make a representation with x, y, and z as a basis. We've got a three-dimensional representation. There's a lot of significance to this representation chemically beyond just sort of the mathematics of making a representation with these matrices, because as you know, the p atomic orbitals basically behave as x, y, and z functions because you have a nodal plane and a change of phase across the nodal plane, right? So we have p orbitals aligned along x, y, and z. They're mutually perpendicular. So there's a positive and a negative, if you will, much like x, y, and z here. So in fact, the threefold degenerate set of p atomic orbitals for any atom located on the Cn axis would, in the C3b, would have this representation. So this will start to have chemical significance. What if I took that further and made a new representation, and I was interested in d atomic orbitals? Could I make a representation with the d atomic orbitals as a basis? Yes, you can. So we have 5, say, 3d atomic orbitals, and we want to make a representation, right? And those d atomic orbitals check my notes. So of course we have xz, yz, xy, x squared minus y squared, and z squared as functions that represent the d atomic orbitals, right? Now if we work out a transformation matrix for x, y, and z, say for a C3, then all we have to do is take the products of xz or yz and so on according to these functions to work out what happens to those points and work out the characters for squares, square type functions that represent d orbitals. Okay? So your transformation matrix now is a 5 by 5 matrix. So I need to come up with a 5 by 5 matrix. I multiply by xz, yz, xy, x squared minus y squared, and dz squared. And I'm going to do a C3 operation counterclockwise. What happens? All right. So if we already worked it out from this transformation matrix. If x goes to x cosine theta minus y sine theta, and if y goes to x sine theta plus y cosine theta, and then if z goes to z, if I just take a product, say xz, it would be this times this, which basically gives us xz cosine theta minus yz sine theta. Okay? So I just multiplied z by these terms. So if xz goes to this, then when I write my transformation matrix, I need to write a set of row values that when I multiply into these column values will give this term. So xz cosine theta minus yz sine theta. Right? And so that means I need a cosine theta, right? And then a minus sine theta. And then every other term in this row is 0. Does that make sense? So cosine theta times xz gives me this, plus minus sine theta times yz gives me this, plus 0, plus 0, plus 0. Right? So I can write a transformation matrix for the 5D atomic orbitals. And all I'm doing is instead of, just using the transformations of x, y, and z and taking products. So you can do this. So then yz goes to, so if I know that y is transforming to x sine theta plus y cosine theta, and I just multiply by z, I get an xz sine theta plus a yz cosine theta. So I just multiply z by both of those terms, right? So then in the transformation matrix, I have a sine theta here and a cosine theta here, 0, 0, 0. So that when I take those row terms and take them into these column terms, I have xz sine theta plus yz cosine theta. Okay? And then xy, go ahead and erase that to make some room. X and y will be the product of these two. So I have x cosine theta minus y sine theta times x sine theta. Let's write that a little bit neater. X sine theta plus y cosine theta. So I'm just multiplying these two. That's the product xy. And then we'll work out this. So we have x squared sine theta cosine theta as the first term of this polynomial. Then we'll take an xy cosine squared theta. Okay. And then we'll do a minus xy sine squared theta. That's these two terms. And then I'll do minus y squared sine theta cosine theta. Okay, so I have this new polynomial. So I have really two parts to this. It looks like I have x squared and xy and a y squared. But remember, one of our d orbital functions is actually x squared minus y squared. So I can group these two together. That's my x squared minus y squared component. This is my xy component. So if I kind of factor this, I have xy times cosine squared theta minus sine squared theta. So I just take these two and pull out the xy. And then I have plus x squared sine theta cosine theta minus y squared sine theta cosine theta. And so if I just pull out the sine theta cosine theta from these two terms, I'm left with x squared minus y squared, right? So these are just trigonometric coefficients for the functions xy and x squared minus y squared. So cosine squared theta minus sine squared theta plus x squared minus y squared times sine theta cosine theta. Right? So now I have my transformation matrix components. So if I put these terms in the appropriate spaces in this row, I'll see that xy transforms to cosine squared theta minus sine squared theta xy. Plus x squared minus y squared times sine theta cosine theta. So that means this term is sine theta cosine theta. And then this is 0. Okay, so when I take these 5 row values and take them into these column values, I get this result in my column matrix, which is what we found here. Okay? So it looks a little bit intimidating at first. But once you work out the transformation matrix for Cn for x, y, z, you can work it out for any of these higher order functions that involve x, y, and z components. And we're actually writing a transformation matrix, a 5 by 5 square matrix for the d atomic orbitals in these crazy functions, right? We can do that stuff. All right, so then we can do the same thing, x squared minus y squared. So if this is x, then x cosine theta. This one takes a longer time to work out because you have x squared minus this one, x sine theta plus y cosine theta squared. So x squared minus y squared. And now we got to break this all out. So if we want to just check where we are. So it's the difference of 2 squares. So we have x squared cosine squared theta is the first term, outer. And then we have minus 2xy sine theta cosine theta, right? And then we have plus y squared sine theta. If I've got that correctly. Sine squared theta. Is that what you said?
Yeah.
Yeah. Yep. So that's the first square minus the second square is going to be an x squared sine squared theta. And then we have 2xy sine theta cosine theta. And then plus a y squared cosine squared theta. Okay? So then you combine all of those. Make sure I didn't mess anything up so far. That looks good. And so if we just take the xy term, we have minus 2xy sine theta cosine theta. And over here we have a 2xy sine theta cosine theta, but we're subtracting. So we have minus 4xy sine theta cosine theta. Okay? And then think not in terms of just the x squared and y squared alone. Think in terms of this difference, the x squared minus y squared function, because that's the one that's of interest to us in terms of the shape of a d orbital. We have the x squared terms. I just want to make sure I'm seeing this. X squared cosine squared theta minus x squared sine squared theta plus y squared sine squared theta minus y squared cosine squared theta. Okay? So then, if I pull the x squared out, I'm just going to carry this down and stop rewriting it over and over. The x squared term is a cosine square theta minus sine square theta. And then if I pull out y squared, it's a sine square theta minus cosine square theta. And here we need a trigonometric identity to go further in the problem. And if you're like me, you don't remember your trigonometric identities, because that was like ancient, whenever you took trigonometry or calculus years ago. So it's like, how can I put these together? This has got to be somehow related, right? Now you could simply just pull out a minus 1 from this side. I guess you don't even need a trigonometric identity. I worked it out with a trigonometric identity out of curiosity. If you just pull out a minus 1 factor from this side, right, then this goes to minus, and then this is cosine squared theta minus sine squared theta. So I just rewrite this as cosine squared theta minus sine squared theta. Okay? And now I have x squared minus y squared, which I can factor out, or I factor out g. And then I'm left with cosine squared theta minus sine squared theta. And you can rewrite that as another way, but it doesn't matter. This works just fine for the transformation matrix. So if I carry that down, I now know that x squared minus y squared transforms as minus 4xy sine theta cosine theta plus x squared minus y squared times this cosine squared theta minus sine squared theta. So then I just put these coefficients now in the transformation matrix to get the product here. So these two terms are 0. This is minus 4 sine theta cosine theta. And then this term here is cosine squared theta minus sine squared theta. And then this is 0. And then the last orbital is easy, thankfully, because z goes to z. So z squared goes to z squared. And look at that. I have a 5 by 5 transformation matrix. And so I'm able to work out how the d orbitals are transformed with a C3 in the point group C3v, or any other point group where you have a C3 aligned along the z-axis, let's say. There's kind of a bit of work to get to this point. Why do we do this because we need the character. We already know that the character for the identity element is going to be 5. We have 5 d orbitals, so the transformation matrix is just all zeros with 5 ones in the diagonal, right? Character equals 5. For the C3 transformation matrix, I need to sum up the values along the diagonal, right? So if theta is 120 degrees, you'll have to plug these into your calculator. But when you work them out, you should have, I don't have my calculator on me. I worked out a character of -1. So I know this one is -1/2 for 120 degrees. This is -1/2. This is 1/4 minus, I think that's 3/4. So that equals -1/2 again. And then this one here is the same thing, 1/4 minus 3/4 equals -1/2, and then 1. So you get a character of -1. And you can punch that into your calculator and just double check. And now when you go to the sigma v, just pick a sigma v aligned along xz or yz. It doesn't matter which one you pick, but then the transformation matrix will be very easy. You'll be able to figure out the character here very easily. So we can do that very quickly. Right, if we just take x, y, xz orbital, yz, xy, x squared minus y squared, and dz squared, the xz atomic orbital is in the xz plane, so it just goes to itself, right? The xz orbital looks like this. Right, so when I do a reflection about this plane, it stays in position. Now the yz orbital looks like this. Okay, so I do a reflection about the xz, it goes to its negative. It's exactly in the same position, but the phase has gone to its negative. The xy orbital if I take this plane as a reflection, I exchange phase. So that goes to its negative. X squared minus y squared a reflection about the xz plane generates the same image. And then z squared is unchanged. So the transformation matrix for this is 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0, 1. So that the character equals 1. Does that make sense? So look at that. You can actually write a reducible representation using matrices and the character of the matrices for using the 5d atomic orbitals as a basis for the representation. Okay? So now what I've done so far in the last 2 lectures is I've shown you that you can use matrices and bases to produce representations in different point groups where the character under each symmetry class is the character of the matrix. of any one of the symmetry operations in that class. They're all equal to one another. All right. Now you can imagine, and I've shown you, that there are a large number of possibilities as bases for making representations. You can make a lot of representations, but there are some that are fundamentally important. In fact, if you look at this matrix, you might notice it can be blocked out into 2 by 2 matrices and then a 1 by 1 matrix. And the fact that this matrix can be blocked out is an indication that this representation can be decomposed to simpler, more fundamental representations. That's what I will show you on Friday, is the fundamental representations in the group. But I wanted to spend the time today to show you how to work out more challenging transformation matrices, say for a C3 or any other Cn that's not a C2 or a C4, right? Because you'll need that skill in order to work out representations. So we'll stop there. Any questions? All right. It's going to take some time for this to absorb into your mind, and it's going to take some work on pencil and paper working this out so that you can get your head wrapped around it. So please don't wait to start working homework problems or just trying some of this on your own, making sure that you can understand these for yourselves. All right? So we'll see you on Friday.